Hi guys, I'm Andrew. I'm here with Megan, Alden, JD, and Anna Katerina, and we're presenting over solid-state batteries. So just as a little roadmap, I'll start with a brief introduction to solid-state batteries in general, and also just some of the drawbacks of liquid electrolyte batteries. And then Anna Katerina will talk about ionic conductivity in solid electrolyte, while Alden will talk about electrical conductivity. And then JD and Megan will talk about some of the challenges facing this battery geometry. Okay. So just to start, what's wrong with liquid electrolyte batteries? So liquid electrolyte lithium-ion batteries are currently the most commonly used rechargeable batteries in most portable electronics, electric vehicles, you name it. However, despite their widespread use, they have a couple of drawbacks, such as limited energy density and flammability. Their weight and instability at high temperatures makes them particularly unsuitable for specific future applications such as electric aviation, which is an industry that we'll have to invest in heavily in order to reduce the emissions of our current transportation sector. However, electric light requires high power consumption, which leads to higher operating temperatures, which degrades the battery faster. And as Maddie mentioned, this will lead to a higher prevalence of unwanted side reactions. This also increases the risk of thermal runaway, which is bad for liquid electrolyte batteries because your electrolyte is flammable. So that occurs when the thin plastic separator between the anode and the cathode is ruptured, essentially causing a short circuit and releasing heat to the neighboring cells. So then that'll cause a dangerous domino effect that'll spread throughout your battery pack and lead to a large, very hard to extinguish fire, like you see in this article below. You guys probably heard of Teslas and other electric vehicles having problems with these fires. And regarding their weight, an electrifying vehicle powered by current state-of-the-art lithium-ion batteries would need to dedicate about half the weight of the aircraft to the battery system, which is just infeasible and uneconomical. So, don't get me wrong, liquid electrolyte batteries have taken us a long way, but to make that next step, we'll have to introduce new technologies, and solid-state batteries might be a way to do that. So their architecture mechanism is actually very similar to that of lithium-ion liquid electrolyte batteries. The key difference is just that they use a solid electrolyte rather than a liquid one, hence the name. They were discovered way back in the 1830s, but weren't pursued as intensely as other battery technologies due to high internal resistances, among other problems. They kind of just didn't know what materials would provide best performance yet. They are currently in use in a couple smaller scale applications such as pacemakers and RFIDs because they're expensive and not fully optimized yet. So in most cases, a liquid electrolyte battery is going to be more practical. Solid electrolyte materials have the potential to address the liquid electrolyte safety concerns because they're inflammable, making them more stable at higher temperatures, thus increasing the range of safe operating conditions and enabling fast charging. Their increased stability also allows for the removal of some of the thermal management hardware that's required for most liquid electrolyte cells, decreasing the overall weight of a battery pack. Replacing the liquid electrolyte with a lighter, more compact solid electrolyte also increases volumetric and gravimetric energy density, which translates into longer potential vehicle ranges and breaking into weight-sensitive industries like aviation. The main challenges that arise with solid-state batteries are regarding the material selection. You need electrode materials with high energy capacities and reasonable volume expansion during cycling so that your battery isn't exposed to high mechanical stresses. You also need an electrolyte material that is chemically inert at the interfaces with the aforementioned electrodes with a high ionic conductivity. Ion conduction is much more difficult within a solid material than it is in a liquid electrolyte because of the processes of diffusion being much slower, which AK will talk about later. Finding the correct blend of materials that maximizes safety, stability, and performance while minimizing cost and being conducive to industrial scale manufacturing is a nightmare. So lithium-ion liquid electrolyte battery manufacturing plants are well-oiled machines, and it would take a long time to design manufacturing processes to produce full-size solid-state batteries at the same scale for the same cost at the same efficiency levels. But my colleagues here will get into the nitty-gritty a little bit more on how the materials for the solid-state electrolytes are selected.
So how might ions be conducted through a solid electrolyte? And for this, we can compare it to liquid electrolytes where we have this classic diffusion model. and see that solid electrolytes actually have various diffusion mechanisms that allow for an ion, such as a lithium ion, to move from one side of the battery to the other side, from one electrode to the other, even though we have more of a rigid structure in between. And it is possible. However, before we do that, let's look at the different types of solid electrolytes that are used. Most research, we have ceramics, which includes oxides and sulfides. And these are really great because they have high ionic conductivity and they're very stable over a wide range of temperatures, but they're also brittle and difficult to manufacture in large quantities. And for ceramics, we can refer to the crystal structure to tell us how conductive that material might be to ions. And we often see that tetragonal or cubic structures often have high ionic conductivity due to the presence of interstitial sites or vacancies that can facilitate the movement of ions through the material. Additionally, high ionic conductivities are related to low electronegativity and high ionic radius. And this is because if we have a lower electronegativity, that means that there's less attraction between, for example, a lithium ion passing through the crystal and the crystal atoms, so that it's more mobile throughout. And moreover, if we have large crystal atoms, this provides us with like a larger tunnel in between it to give a bigger pathway or easier access for that ion to pass through. So here, that's our little, or large tunnel rather. Next, we have polymer electrolytes. And these, even though they have lower ionic conductivity, they are often flexible and they can be made into different thin films or shapes. But this low ionic conductivity more recently has been addressed by a post-tech research team, which created a block copolymer of polystyrene sulfonate and polymethylbutylene. And this had the ability to self-assemble into a specific structure to optimize the properties, such as ionic conductivity and stability. So I would say let's not write off the polymer electrolytes just yet. And in addition, we have composites, which are some combination of polymers and ceramics, where researchers can tune the characteristics that they want. Also, a special mention to garnet electrolytes, which is a family of ceramics. And the one that I'm showing here is lithium-7 lanthanum-3 zirconium-2 oxide, which has a high degree of order and symmetry, with the oxygen octahedra forming a network of interconnected tunnels that allow for the lithium to pass through it more easily. So how do the ions actually diffuse through the solids? This really depends on the type of electrolyte that we're looking at, and I'm going to focus mostly on ceramics. But all of them really rely on an energy landscape where the ions are passing to a more stable configuration, but must overcome this energy barrier in order to do so. And this is really related to how we discuss p-type and n-type materials, where the Fermi level difference creates a net flow of electrons. And in this case, it's applying to the movement of ions. So here, the difference in chemical potential between the anode and the cathode electrodes is what's allowing for the ion movement to occur. And this gradient is what drives the movement of ions through the electrolyte. And in literature, you'll also often see it referred to as hopping. And that just means basically the movement of those ions from like one site to the other. The first one would be vacancy hopping, where if there's a free space, the ion can just move right into it, and that will leave another free space for another ion to move into it. Then we have interstitial hopping, which is similar, but it occurs between the atoms of the crystal lattice. And then lastly, we have substitutional and interstitial mechanism, where, for example, we have some ion passing through, which is in an interstitial site, and it will move into or replace a atom in the lattice and kick this one out. So it's like a combination of these different mechanisms. And if we're talking about polycrystalline ceramics, which means that there are lots of different grains and thus grain boundaries which are making up the electrolyte as compared to just like one orientation of crystal. We also have different ways for the ions to move through it. And this really depends on the resistance of the grain versus the resistance of the grain boundaries. So often the ions will take a combination of different pathways, which include like passing just in between the grains or passing through the grains. And lastly, for polymers, we're looking at something called segment motion, which really relies on the mobility of the polymers in order to facilitate the movement of the ions throughout. And in this case, we have polar groups within the polymer, which enable transport. And the ions will basically hop between the coordination sites along the polymer chains. In this case, the rate of ion transport is directly related to the concentration of the ions and the segmental mobility of the polymer chains. Typically, this segmental mobility occurs around the glass transition temperature. So we looked at how the different types of electrolyte affect the ionic diffusion through the solid electrolyte, but there are also other factors which will influence it, such as temperature. The ionic conductivity of solid-state battery electrolytes typically increases with temperature due to greater mobility of ions at higher temperatures. However, at excessive temperatures, it can also cause thermal instability and reduce the lifetime of the electrolyte. Here we can see in this diagram a pretty linear relationship between increasing temperature and more mobility. Next, pressure. If we apply pressure, it increases the contact area between the electrode and the solid electrolyte. And this basically promotes ion transport. However, high pressure can also lead to mechanical failure and reduce the durability of the electrolyte. And then lastly, we have doping. By introducing dopants or impurities into the solid electrolyte, it can alter its ionic conductivity by modifying the crystal structure, electronic properties, or defect concentration. Here, the researchers performed various dopings on that garnet electrolyte that I showed earlier, and they found that the best total ionic conductivity was achieved with multi-doping that garnet electrolyte with aluminum, tantalum, and fluorine. And basically, they concluded that doing this stabilized diffusion intermediates and provided vacancies in order to promote ion flow.
In addition to being ionically conductive, we want the solid electrolyte to be electrically insulating. And why that is because if there's ion flow through the electrolyte, we don't want the electrons to also be flowing through the electrolyte. They could recombine with the ions and then defeat the purpose of the battery. But also we need them to be flowing from the anode to the cathode, because that flow of electrons is how we're harnessing the electricity. So if they're flowing through the electrolyte, that means they're not flowing externally through the circuit, and then there's not much purpose to our battery. So I'll lead you through the slide, don't worry. When we're looking at our common solid electrolytes, are they what we expect them to be? Well, we expect them to have a large band gap. And why is that? Large band gap means they're an insulator. We want an insulator, something that does not, an electrical insulator, something that current is not flowing through, electrons are not flowing through. And if we look at some common solid electrolytes, this paper just took a look at a bunch and characterized them. Their band gaps are between usually 4 and 7 electron volts. And this aligns with what we'd expect. Semiconductors are typically usually the cutoff for what's considered a semiconductor is below 3.2 electron volts. These are way above that, meaning they're, even if you add some energy, it's going to be really hard to excite a significant amount of electrons up and hop that band gap. For reference, silicon is like 1.1, 1.2 electron volts. So they have a very large band gap. And how does that affect their conductivity? Well, as we'd expect, they're not very electrically conductive, which is what we wanted. So at room temperature on the y-axis, we have room temperature electronic conductivity in the units Siemens per centimeter. Siemens is inverse ohms. And we see that they have very, very small levels of electronic conductivity. So on the scale of, on the high end, these ones are at like 10 to the negative 5. On the low end, they're at 10 to the negative 10, which is not very much conductivity. And again, for reference, something that's very conductive would be copper, for example, and its conductivity is on the order of 10 to the 5th Siemens per centimeter. And something that's not very conductive that you might know is window glass, which is 10 to the negative 10 Siemens per centimeter. So these have large band gaps, are not very conductive, which is what we want. And to kind of gut check that against other concepts we've learned, what they physically look like. This is a slab of, there's a little bit of lithium phosphate, and its band gap is 5.75 electron volts. And sure enough, it looks white. So most solid electrolytes look clear or white, and this is because they have a really large band gap, meaning they can't absorb, they're absorbing mainly in the ultraviolet range, and reflecting other things. So what we're seeing is what it's not absorbing, which is the whole visible light spectrum, essentially, which is why it looks white. So that kind of checks out. And how do we characterize these materials generally? Well, again, they're not very conductive. They essentially are acting like a resistor. So the way we'd characterize the resistor, for example, is you could use like a multimeter. And the way a multimeter would work is you like have two little probes and it injects a small current. And then you can use Ohm's law. So you know how much current you put in, you're measuring back the voltage drop between your 2 points in the circuit, and Ohm's law can spit back the resistance for you. The way we characterize batteries generally when we're looking at things like conductivity and resistance is people often use a technique that honestly is quite confusing. There's imaginary parts, but it's called electrochemical impedance spectroscopy. And what you can see, some people will do this in operando too. So like as a battery is running, they'll take this EIS measurement. And you can see, like, if we're looking at that little red dotted line where the semicircle ends on the x-axis as you go around, that is an important measure of the impedance of the battery. And as the battery degrades over time, you'll see that circle get kind of wider and farther, which is an indication that the battery is degrading. And where do problems arise in the context of electrical conductivity? Two things. One, self-doping via native effects, aka like the intrinsic or the native defects within the material right when you put it in, not like a degradation effect, can lead to effects that people call self-doping. So that can make it more conductive than you want, which decreases the performance of your battery. But secondly, you want to be careful about decomposition products. So as your battery runs, if it starts to decompose into products that have electrical conductivity, that can lead to, again, like hurting your battery's performance slowly, or if there's some sort of electrical pathway, conductivity pathway between the anode and cathode, that can short circuit your battery and it'll stop working. Moving on to the next part.
Great, thanks, Alden. My name is JD, and I'll be going over the research challenges that need to be overcome in order to make solid-state batteries a viable technology. First and foremost, we need to figure out what the electrolyte is that we want to be using in solid-state batteries. But even once we figured that out, we would need to have a much better understanding of what the interactions are between that electrolyte and the anode and the cathode, particularly at the interface with the electrolyte, because as we'll see, it's at this solid electrolyte interface, or SEI, that we get a lot of tricky behavior that we need to work out in order to make solid-state batteries viable. So there are two areas that I want to touch on regarding challenges. The first being picking the solid electrolyte, and the second being what happens at that electrolyte anode interface. Let's start with the solid electrolyte. So there's a long list of properties that we would want in a solid-state electrolyte. The first and potentially most important is what's called a wide voltage stability window. In other words, this is the voltage at which a battery can run, in which the electrolyte neither reduces nor oxidizes. In a typical electric vehicle, as of today, that runs at about 3 to 4 volts. So we need to have a wide range in which the battery can operate without the electrolyte oxidizing or reducing, which would be bad. And as Alden and AK have already mentioned, we need that high ionic conductivity, but basically negligible electric conductivity. And what I'll be focused more on in this part is why we need there to be good mechanical, chemical, as well as thermal stability. And then, as Andrew mentioned in the introduction, it can't be flammable, and of course, we want it to be cheap. It's really hard to find a solid electrolyte that has these levels of ionic conductivity that we need, because as AK already mentioned, when the electrolytes are basically frozen in place and can't move, the ions can only move through vacancy and interstitial hopping. So when we look at measures of conductivity in liquid versus solid electrolytes, measured in Siemens per meter, you can see that a liquid electrolyte usually hovers around 1/2 to 1, while solid electrolyte is orders of magnitude lower than that. Even the highest ones we've achieved in a research context, looking at 10 to the -2, 10 to the -3 Siemens per meter. So this is the first and most difficult challenge that we would need to overcome. The second really key point is that cracks in the solid state electrolyte are one of the most common failure points in these solid state batteries. Cracks seems pretty intuitive, but they lower coulombic efficiency. They can cause shorting in the battery. And so these batteries need to be able to undergo certain levels of mechanical stress, thermal stress. I'll talk about stack pressure in a few slides. And they need to be resistant to dendritic cracking. And this is what I'm going to focus on now. Maddie covered this a little bit in his lecture, but I'll just expand on it a bit. So there we see a lithium anode and SEI, that's what I mentioned, solid electrolyte interface. And effectively what happens is as we start running this battery and lithium gets redeposited on that anode, it's not going to perfectly redeposit in some sort of perfect flat plane to reconstitute that initial nice rectangular shape of lithium. It's going to redeposit kind of in odd places, causing those places to grow unevenly. As we get that volume expansion, it's going to cause cracks in that solid electrolyte interface. As that plating process continues, we start to get lithium dendrites. And here's a nice little image of what that shows. So we see here a lithium dendrite penetrating into the electrolyte, causing a crack. From there, things only get worse. We can have bits of lithium that actually get trapped in the solid electrolyte and never redeposit onto the anode. And this basically just kills our capacity of our battery. And this is what it looks like in TEM. So as you can see, as we cycle more current through the battery, we get these long cracks in the solid electrolyte. There have been some improvements in this front in basically two ways. The first is by using ductile materials. So lipin, lithium phosphorus oxynitride is a commonly researched electrolyte. And as you can see, what happens is when you try and crack it, it acts ductile. It actually just gets more dense in some places than others and relieves that stress by shearing. Similarly, other researchers have experimented with putting Kevlar into these solid electrolytes, and these Kevlar bits prevent the propagation of cracks through the electrolyte. Now I'm going to move on to the electrolyte anode interface. So in a normal lithium-ion battery, right, we've got sort of slurry on either side of the separator, which makes a nice contact with the separator. In a solid state battery, the issue that we get is one of what is called wettability, or basically the ability for a liquid to maintain contact with a solid, or potentially in this case, two solids to maintain contact with each other. Obviously, if you imagine, it's like if you put two big pieces of metal on top of each other, they're not going to be perfectly touching in all planes. And so you get these gaps in between. And these gaps mean that the effective interface between the electrolyte and the anode, lithium metal in this diagram, is actually quite low, which makes for high resistance and means it's really hard to have ion transport across that boundary. This space also creates a space charge layer, also known as a depletion region, which is what we looked at in class, where we basically have no free carriers, free charge carriers right at that boundary. This also lowers ionic diffusion and increases the overall internal resistance of the battery. And the last thing that can happen is this goes back to the thermal stability point I mentioned. As we cycle the battery, it goes in through maybe different weather conditions. We're going to have expansion and contraction due to temperature increases and decreases in that electrolyte. And what can happen is the electrolyte can actually start sort of shrinking away from the anode, and we get these spaces here. And the issue with that is the same as the wettability problem. We would get high resistances and very difficult for ions to be transferred in that scenario where there's not good contact between the anode and the electrolyte. Now, one way that we've dealt with this so far is we just apply pressure into the whole battery stack. So we effectively squeeze it. And this can prevent this wettability issue, right? You can imagine if you really squeeze those two plates of metal together, you're going to have better contact, which can lower resistance and improve the overall efficiency of the battery. But to go back to a previous slide, the issue with that, this is what I mentioned earlier with stack pressure. As you increase the pressure on the battery stack, you're also going to increase the likelihood and the sensitivity to any kind of mechanical stress that might cause a crack in that electrolyte. So it's a bit of a double-edged sword, where squeezing it together can reduce the wettability issue and reduce the likelihood of voids, increasing resistance in our battery, but it also makes it more susceptible to cracking. And now I'll pass it off to Megan to discuss commercialization challenges in synthesis.
Hi, everyone. I'm Megan, and I'm going to talk to you about one of the more applied aspects of solid-state batteries, which is their synthesis and manufacturing processes. To begin, I'll remind everyone of the basic structure of the solid-state battery. As Andrew mentioned previously, solid-state batteries are composed of a cathode and anode separated by a solid electrolyte. Lithium ions travel from the cathode to the anode through the solid electrolyte. The video on the right shows the basic charging and discharging operation of solid-state lithium metal batteries. You can already see from this video that solid-state batteries are more complicated to maintain because of their expansion and contraction when charging and discharging, which I'll touch on a bit more later. And I'll play the video again so that you can see. First, I want to discuss deposition methods often used to synthesize solid-state batteries. Currently, there is no conventional method of synthesizing solid-state batteries because although solid-state batteries have been successfully manufactured by a few startup companies, large-scale commercialization of these batteries has yet to occur due to the cost and the difficulty of these manufacturing processes. Manufacturing processes of solid-state batteries need to take into account a few challenges, so I'll first summarize them here. The first challenge is that the anode, cathode, and electrolyte layers need to maintain consistent contact. Because there is no liquid electrolyte that will automatically fill the flatness deviation present on a surface, oftentimes high pressures are required to press the solid layers together for adequate contact. Speaking of high pressures, the second challenge is ensuring that the mechanical stress of this high pressure won't cause cracks in the solid layers. And finally, the expansion and contraction of the battery due to solid ion transport, leaving volume vacancies in the cathode, means that pressure between layers can't restrict movement of ions. Examples of the most common deposition methods include atomic layer deposition, or ALD, which we have discussed in class as a method of depositing single layers of atoms consecutively. The cathode, solid electrolyte, and anode, along with any productive layers, can be manufactured with very few defects in this way. Similarly, molecular layer deposition, or MLD, allows for both organic and inorganic molecules to be deposited in a similar manner. However, this method is extremely slow and therefore expensive. On the contrary, processes such as dry pressing allow for a much faster deposition, but the lack of control over synthesis conditions such as temperature and uniformity can greatly influence the formation of defects in the solid electrolyte, as well as alter the grain boundary morphology, or in other words, the layer interfaces. Clearly, there are many possibilities for deposition methods of layers of solid-state battery materials, and each has their own advantages and disadvantages. I could talk about this for a while, but in the interest of time, I want to move on to bulk manufacturing of solid-state batteries. In Maddie's battery lecture, he mentioned several methods of stacking and winding for regular lithium-ion batteries when manufacturing in bulk. In solid-state batteries, the primary method of stacking is simply single-sheet stacking. I've not found any research on other methods of bulk manufacture, likely due to the complexity added due to the expansion and contraction occurring from ion transport, but it is currently not a primary focus of research and will likely be optimized later down the line. It seems like with all of these uncertainties in the manufacturing processes that solid-state batteries are not ready to hit the market. However, many companies have already created products using solid-state batteries. An example of this is a French company called Bolloré, which in as early as 2011 created and sold an electric vehicle called Blue Car that utilized a lithium metal polymer solid-state battery. To create their battery, ultra-thin layers of metallic lithium foil anode, solid polymer electrolyte, organic cathode, and aluminum foil current collector are layered, coiled, and compressed into a prismatic shape and assembled into battery cells. The vehicle itself was a small two-seater vehicle, and its battery had a capacity of 30 kilowatt hours, equating to a range of about 150 miles. Comparatively, a Tesla Model S with a liquid lithium-ion battery has a capacity of 100 megawatt hours and a range of 400 miles, although it was developed several years later, obviously. The solid-state batteries in the blue car were considered much safer than liquid lithium-ion batteries, and only a few fires occurred because of vandalism to the vehicle, so not even because of the battery itself. The expense of the car and lifetime of the batteries was also an issue, but regardless, several thousand cars were sold. More recently, another startup created a 6,000 milliamp hour solid-state battery that is the same size as a regular 4,500 milliamp hour battery used in a cell phone, meaning that it will have a much higher charge density without increasing the size or weight of the phone. Cost and manufacturing of the battery are still a limitation to it being fully deployed, though. There are several startups working on this, working on solid-state batteries as well. Solid Power is a solid-state battery startup that has produced several prototypes and is expected to sell its batteries this year, with solid-state batteries for vehicles being released later in 2026. QuantumScape is a startup from Stanford that is known as one of the leading companies researching solid-state batteries. They recently announced that they overcame the problem of dendrite formation at high charging rates, which is a huge breakthrough that other companies haven't quite reached. Ampsera is another leading company that focuses more on producing the solid-state electrolyte materials rather than the full battery itself. So yeah, although there are still many challenges surrounding the development of solid-state batteries, recent breakthroughs that these companies have made allow for solid-state batteries to be the next big shift in energy storage that is expected to occur in the next few years. And it will be an exciting transition to watch. I'm going to pass the mic off to Andrew to give us some final thoughts.
All right, so just to recap, solid-state batteries have the potential to give us substantial improvements in energy density and safety due to their lighter, more compact nature and the fact that the solid electrolyte material would be inflammable as opposed to the flammable electrolytes in most modern day lithium-ion batteries. However, we still need to find a way to, figure out the tangled web material section that'll give us high ionic conductivity, lots of durability so that they can withstand the mechanical stresses of everyday life. And then also finding a way to simplify the manufacturability so that these things can be produced on industrial scale in order to match the demand of the future. Yeah, thanks for listening, guys. Here are our bountiful references. Yeah, see you in class. Excited to take your questions.